Pharmaceutical companies such as GlaxoSmithKline synthesize, that is make, many thousands of chemical compounds each year in their search for new, safe and effective drugs to treat disease. The sources of ideas for new drug compounds are very varied. They include materials found in plants, as well as modifications of existing drugs, and materials occurring naturally in the human body. Increasingly, however, scientists start the search for a new drug with an understanding at the molecular level of the disease that they wish to treat, so they may be able to predict the structures of chemicals that might affect the course of the disease. Computer modelling is a vital tool in this process. X-ray diffraction allows chemists to work out the three-dimensional structures of complex molecules and to make models of them, either real models or computer models. Some computer graphics can be viewed in 3D with special glasses. Here, a crystal of an enzyme is being examined by X-ray diffraction. It is rotated in the beam of X-rays. X-rays scattered from it interfere with each other and produce a pattern of spots called a diffraction pattern. From this, computers calculate first a map showing the distribution of electrons in the enzyme, an electron density map, and then the enzyme's 3D structure. Modern computers have changed the analysis of X-ray diffraction data from a slow and laborious process into one that is routine. Computer software allows a structure to be viewed from any angle. It can be shown in different ways: ball and stick, space filling, and skeletal. Different elements are represented by colours: grey for carbon, red for oxygen, dark blue for nitrogen, and so on. This view shows the so-called van der Waals surface of a molecule. This has been coloured to show polarity: delta plus areas in blue and delta minus areas in red. This is the best indication of the molecular shape. One of the first drugs to be developed using computer modelling is GlaxoSmithKline's flu treatment. The process of designing this drug started from an understanding of how the flu virus attacks human cells. The flu virus first sticks chemically to the outside of a human cell, then enters it and replicates inside. The new viruses burst out. At first, they stick again to the outside of the cell, and before they can infect other cells, they must release themselves from the original cell. They do this using an enzyme called neuraminidase that breaks the chemical bonds between the virus and the cell. If neuraminidase can be stopped from working, the new viruses cannot break free to infect more cells, and the disease will not spread. The structure of neuraminidase is known from X-ray diffraction. This is its active site. The chemists needed a compound that would bond to this active site and block it, thus deactivating the enzyme. The drug would be an enzyme inhibitor. Normally, neuraminidase active site bonds to a molecule called sialic acid, which is found on the surface of the flu virus. The computer modellers wanted to find a molecule that would bond to neuraminidase better than sialic acid. So they investigated the effect of making small changes to the sialic acid molecule. They found that the enzyme had an acidic group in its active site. They therefore predicted that a variant of sialic acid containing a basic group should bond strongly to the enzyme. The computer model confirms that the prediction is correct. They tried a more strongly basic group. The computer model predicted even stronger bonding. This molecule bonds so strongly to the active site that it blocks it and deactivates the enzyme. The flu virus cannot cut itself free from the cell wall and so infect other cells. This is sialic acid, and this the enzyme inhibitor used for flu treatment. Note the overall similarities between the two molecules and the important differences. Of course, the compound still had to be made. Firstly, in small amounts to confirm the results of the computer modelling that it really did inhibit the neuraminidase enzyme. Then in larger quantities for tests on safety and eventually for clinical trials on actual patients. Clinical trials have shown that the medicine can reduce the recovery time from flu to 3 days rather than over a week without treatment. And it is now being used around the world.